My name is Ben Jackson. I'm an applications engineer with NH Research in California. Today I'm just going to take you through some of the fundamentals, some of the test equipment that we manufacture, and some of the ideas of selecting the right tools for the right job, and things to look for, and some industry examples of that. So getting started, who we are, NH Research, if anybody's familiar with us or they haven't heard us. So we're a privately owned company, veteran-owned, up in Irvine, so not too far away from here. And that's where we do all our production, all of our manufacturing, all of our software applications, all there. And we really specialize in AC and DC electronic loads and sources, as well as the software to go along with those and control them. We've been in business for over 50 years, same owner. And we service a lot of industries, everything from electric vehicle manufacturing, a lot of testing, design, engineering, characterization, and then also military aerospace, pretty much everything in between. So to get started here, because we are electronic load, AC, DC source as well, some of the things I want to kind of get out of the way first is kind of defining, what makes a source, what makes a load, and we'll kind of carry this throughout the presentation as well. Just because sometimes where that kind of get confusing is if you're working with bidirectional type loads, sources where the current can go both directions, it helps to definitely identify if we're dealing with a source here a little bit. And it's a common question we see come up with some of our customers as well. So getting started, what we define a source as is where the primary control loop is the voltage, or for AC the frequency as well. And then for the load, the primary control loop controls the current. And then unity AC, all your voltage, all your current are aligned, including the harmonic all in phase. So it's all pretty straightforward as well. So the one thing that the above doesn't cover, that doesn't cover what direction the power is going. So for that, we're going to assume that a positive power factor is when a source is generating power and when a load is absorbing power. So with kind of just like those basics there. Kind of the question I kind of have to you, and I'll give the answer as well, is if I was to give you kind of the question of what is a grid-tied inverter, and given these definitions, would it be a source or would it be a load? And kind of the way to think about that is, well, if it's a grid-tied inverter, that's what your UT is. You know it's connected to the grid, and you know the grid is a voltage and frequency control device, so the grid is a source. So as such, the grid-tied inverter needs to be a load. But then now, would it be a positive or a negative power factor? That's going to depend then on which way your power is going. Are you going to be pushing power back onto the grid or pushing it back on or off? So there's some things to think about. So traditional sources are not bidirectional. These are, you have your traditional AC or DC source, and they just push the current in one direction. You have, I don't know, name any AC source. And as such, if you have a UT that wants to push any type of power backwards and backdrive, which some of you may be familiar with that term, that typically doesn't work out very well, or some of the sources have a very limited amount of energy that they can backdrive. So a possible solution to that is if you're doing like some sort of system type setup, you can add a load to your source as well, or some sort of resistor, some way to absorb that back energy. So that's a possibility. But then some of the things you have to look for into that in some of your systems, higher cost, more complexity. And this is kind of where certain things like the bidirectional AC and DC products come into play, and this is what we're going to be talking about here in this presentation as well, and something that we manufacture, where you have the battery emulators, which can do the DC current either way, or they essentially act like a battery, where you can think of the battery in your car. You can power all of your accessories inside your car, your lights, and what have you. But at the same time, you have your alternator that can push power back onto your battery as well. And the same thing with the grid. If you have DC solar panels at your house, they can put power, into your house. But at the same time, if you have excess power, you can export that back onto the grid. So it can go both ways. So with that, NH Research, we'll go into it here in the next couple slides too, just kind of give you a little background. We do have some products, the 9200s and 9300s, that do actually provide this bidirectional two-quadrant operation where you can actually use them as a standard source where your current's just going to go one direction, or you can use that as a load where your current will just come in one direction as well. Or at the same time, you can also set it up as a battery with actually a series resistance that we allow you to program. And this is where then current can flow both ways, just as with a battery. And that's one of the neat features too with the 9200 and 9300 of ours that we'll go into here in a little bit, which is where that programmable resistance, similar to like kind of like a Randall's model, where you have that mechanical resistance, you can emulate that for voltage drop for your IR. And so here we have it, 92 and 9300s. There on the right, 9300s and the 9200s here. 9300s are kind of like the big brother to the 9200s. These guys are built up in 100 kilowatt building blocks, and the 9200s are in these 12 kilowatt building blocks. But you know, one of the, there's some of the ranges as well. So, I mean, really you can go, and you can actually go lower than 20 volts. We have the lowest voltage range is 40 volts, then all the way up to 1200 volts, and then all the way up to 1.2 megawatts by paralleling them. And one of the neat features of both of these is they're really fast current rise times, transient response times. So for the 9200s, for example, if you want to do some fast transients, you can go your 10 to 90% current rise time in about 400 microseconds. Which when you think of, you know, like a standard DC source, you know, maybe you're thinking in the 1 to 10 to maybe even hundreds of milliseconds. So the ability to do those fast transients is there. Then the other thing I want to talk about too is on the AC side. And this kind of gets into some of our other products too that will go in here in the next slide, I believe. And that's the grid simulator. So we kind of talked a little bit about the DC side going both directions, emulating a battery. But with the AC, this kind of comes into play as well, especially with a lot of the EV stuff in the market now. Some manufacturers are starting to do stuff like vehicle to grid, where vehicles can push power back onto the grid. But then also there's certain standards like the IEEE 1547 and the UL 1741, where you have to test, you know, to a certain percentage over nominal of your voltage. And as such, depending on what voltage range you're in, you know, for example, if you're doing the US single phase 120 or three phase 480, what that means is if you're going to be using a grid simulator or an AC source to do this voltage type testing, you need to have a source that can go 20% above what it is you're testing. This is one of the reasons why we'll get into the 9410 grid simulator, which shows 350 volts line to neutral for the range. And this allows for the full testing of the IEEE 1547 if this is something that you guys are interested in doing. And then on top of that, with the 9410, and then also pretty much all of our other products, high resolution data is measured internal. So where normally you have maybe some external DMMs or oscilloscope type functions, equipment that you have to have on test, those features are built into the 9200s and the 9400s for the AC and DC. That's up to 1.2 million samples per second. Okay, and so here on the 9410, for example, on the grid simulator for doing IEEE 1547, this comes a lot of EV testing for doing EVSE type stuff, also any of the grid tied inverters, solar, for example, which is going to be used as an industry example in the next slide, I believe. Using the ability to have that higher 350 volt line to neutral allows that. And then also the precise voltage resolution, the NHR products, the 9400 specifically has the 0.005% voltage resolution. And then the ability to go up to 880 hertz. So this also helps in the military applications, where you'll typically see 400 hertz is the common AC frequency. So with this product, you can also do those. And In fact, the industry example we're going to be using later it is actually an aerospace example where it was done at a few different frequencies, but 400 hertz included. The other thing too is the different configurations. So when you're doing your testing for AC, it's a little bit different than DC where you just have a DC bus. AC, you have to think about, are we going to do a single phase? Are we doing split phase with a center tap neutral? Are we doing three phase? Maybe we're doing AC and DC. And that's one thing that the 9410 grid simulator can do. You can actually set it up for either single phase, split phase, center tap neutral, three phase. You can do AC and DC at the same time. You can even do things like put individual harmonics on individual phases, for example, or do phase dropout on specific phases. Right there. And these are just some examples of some of the abnormal wave shapes you can do with the 9400. And one of the things too is the ability, the 9400s, you can make voltage changes on your wave shape in about 60 microseconds. It's about how fast you can make a change. You can do those sub-cycle, sub-degree even changes to frequency. So here's kind of an example we did, an industry example, where you kind of see in the middle we have some inverters, grid-tied inverters there. And on the right-hand side you actually see 9200. This was doing the PV emulation. And then here, this is actually the grid simulator. So this is again as the grid, as the voltage. And that's a 9410. And this customer has actually used our equipment, the 9410 and the 9200, to do the IEEE 1547 testing. And then kind of just as like a third-party verification, everybody's familiar with like a Tektronix scope. So being able to do the voltage drop, sag, and then basically seeing the current and what the current's doing. With IEEE 1547, depending on the length, duration, magnitude of that voltage drop, you have a certain amount of time that you have to stop driving current back onto the grid. So this is something that we're able to test. There. So this is actually kind of a new product. It's been out for a little under a year, kind of the first of its kind. This is the 9430 is a 4-quadrant AC load. I think typically people are used to on AC loads doing the linear, so you can't do the true -1 to +1 power factor. The 9430 is a true 4-quadrant load, so you can do your full -1 to 1 power factor. You can shift around your power factor everywhere in between there, and it simplifies in the fact that you don't need to have any of these external components, your inductors, your capacitors to do that. So it really simplifies that type of test. And then included in that is the built-in harmonics editor. So you can go up to the 50th harmonic. It's got about a 3 kilohertz drop-off. So if you're in like the 50 to 60 hertz range, then you can go all the way up to the 50th harmonic. But even on. And then you also can make your own wave shapes as well. It's got a little graphical editor. You can just use a mouse and draw on there as well. But definitely the ability to do those custom wave shapes and change them on different wave shapes as well, on different phases. So you can have, your A phase has some crazy harmonic, and then your B and C can be perfectly fine. Or maybe your C has complete dropout. Those are all things that are possible. You can also do resistant type loading where you follow the voltage, pretty standard. But then we also give a series RL loading where you can actually give an inductive value and load that way as well. So again here, here's a wave shape of actual data collected during testing of doing, I believe this was a 0.75 power factor. And here, this was verified by actually Yokogawa. This is a WT1800, where you can see, 0.75 to verify that. And then also going on to the fact that with the built-in measurement capability of the 9430 and all our other products, we give you access to all that raw data. So another thing you can do, like here for example, I was doing some FFT analysis in Python with it, so I was able to actually pull that data out as well. And for example, this particular customer, they were doing this testing, and in the past they were using a load with a big kind of fixturing with a bunch of inductors and a bunch of capacitors on the output to give them kind of this inductive shift or capacitive. And so by being able to use the 9430, they were able to completely simplify that testing. It really reduced the test time. And then also just all the added extra components, the relays for switching in this fixture. So the one other thing I want to talk about too was the regen aspect. Some of our products, the 92, the 9300s, the DC and AC, they're also regenerative. So this means that instead of traditional linear loads where your power just kind of goes to heat and that's what it is, and the power company thanks you at the end of the month. With this, you actually can save up to about 94% of that power and put it back onto the grid depending on our product. And so this is something you see here. You have your utility here, some storage here, maybe some sort of UUTs here that you're loading. And if you think about it, we could replace the utility side with one of like the 9410 grid simulator. The storage you can replace with some sort of 9200 like a DC, doing like a battery storage. And then you have our loads here. And for the traditional non-regenerative, where power just kind of goes one way, you can kind of see it follows around here. Your AC comes in, you have your source, powers your equipment, goes to your load, and burns off here, and that's it. But with regen, now you're burning off, instead of burning off your power, you're actually putting it back onto the grid. So really what you're seeing here at the grid, what the grid power company is seeing is really just the net loss of the system. And we have done some studies with some customers where we've actually seen them and had them report to us pretty large savings, dollar amounts. That's definitely more typical if with customers who are doing like large burn-in type testing, where you just have long tests going over long durations of time. But that is definitely a byproduct of the regen. Little graphic there. Let's see. All right, so with these, the new tools, the 9200s, the 9300s, the 9410s, the AC, what it really does, it definitely improves on the testing efficiency, especially things with like the 9430, where now you can do the true 4-quadrant. You don't have to have the external fixturing, the inductors and capacitors. Then also, the bidirectional DC, where maybe in the before, if you wanted to do bidirectional, you'd have to have a source and a load. You kind of have to switch between them, and you'd have to have some software to control that just right. And if you were wrong, you may damage some equipment. So the ability to have something that can handle that for you automatically, like the 9200, 9300, 9400, really does save a lot of time in testing and efficiency. And then also the operating costs, the regen for the utility side. And then, with the fixturing that we talked about, the eliminating all this extra equipment that you would need to have. And then less time per test, where typically, maybe you have a test, like I was saying, that you have, you're constantly having to add stuff on, take it off, retest, and et cetera, and now you can kind of just automate this all. Definitely saves a lot of time, so it's definitely something to think about. And we're constantly having new products come out, higher power, larger ranges. So there's something that if you saw anything here, products that maybe interested you, AC or DC side of things, or some of the capabilities of what it is we offer, I definitely encourage you to ask me. I may not have all the answers, but I probably have some of them and point you in the right direction. And I think that pretty much concludes the presentation. Now we can all do the raffle?
Yeah, we have a little time for questions if anyone has any questions.
On the source as the output, is the last stage digital or is the last stage analog?
For which product?
On the source side, on your instruments.
Yes.
On the really driving, the power driving side.
Yes.
Is it the digital, creating with digital the power, or you're creating it through an analog amplifier?
So the last stage is an analog stage, and we do have the digital control, so it is a full closed loop.
That's I assume.
Yeah. Yeah, but we do have actually some interesting features on that. We have what we call regulation gain, which is an adjustable feature that we allow the customer to have. And what it allows you to do, it allows you to either completely eliminate that DSP control. So if you just want to go at hardware speed and let the hardware do, then it'll do that, but you lose that closed loop. And maybe you have oscillations, but it will give you the fastest absolute. But then also we allow you to kind of adjust that as well. You can actually slow down or speed up how fast our DSP responds to voltage changes, for example. So we give you that control. Or you can just leave it default. Most people do that. But it kind of depends on what your UT is. Because sometimes, like if you're using us as a DC source, and we're powering a piece of electronics, and it has its own switching on the input, maybe for whatever reason, because we're at about 60 kilohertz, maybe you're at 60 kilohertz, we'll get some weird oscillation. So the ability for us to kind of slow that down, we can dampen some oscillations or overshoots or stuff like that as well.
Because by other customers, they're making that digital output, and the harmonics which creates interferes with the electronics which we want to test.
Mm-hmm.
So we don't get right results.
Yeah.
An analog output, we know we're feeding 50, 60 hertz in.
Mm-hmm.
That's what you will see on the mains test, and not. Yes, you see all the junk too in the normal main, but not for test purpose.
Yeah. Yeah.
That's the question.
That's a good question.
Yeah. Any more questions, or with that, thank you so much. All right. It's not a bottle, it's a bottle of something, but it's not alcohol.